Good afternoon, everybody. I'm Payman Byron, and we're very glad that we have you here today. Before I hand over to our presenter today, Mr. Manilal, I just like to welcome everybody to first lecture of lecture series that SAICE Structural Division is planning to present for this year. And would like to invite you to bear with me just for a few minutes to take you through SSD and what is it all about and what are our plans for this year. But before I start, something I have to mention. If you have any questions or you like to raise any points to the presenters, please use the Q&A button versus the chat button. So then we know exactly the questions that you're raising, and then we'll pose it to the presenters. If you have difficulty finding the Q&A button, if you move your mouse to the bottom of the screen next to the chat, there is another button which allows you to post the questions. Okay, back to SAICE Structural Division. For those that might not know, we had a joint structural division, which was a joint venture between SAICE and iStruct-E of UK. And in 2018, iStruct-E, due to strategic reasons, they decided that to have a standalone foothold in South Africa. And they separated from SAICE. And with that, in 2019 was when SSDChair Structural Division was born. In terms of us being a new division, well, not so new, considering the 8 years of the history, but when I say new, I mean this new entity called SSD. We have rebranded our logo. As you can see, there is a logo on the top right of the screen. And with that, we are strengthening our presence in social media. So at the moment, we have an Instagram page, a LinkedIn page, Facebook, and we are planning to have a YouTube channel soon. As part of long-term plans, we intend to host university talks. So we are in the process of engaging the various universities, and we're planning to invite the academia, the heads of departments from the universities to sit in our committee, and we plan to roll out prize giving to top students in the structural sector, in the structural field in various universities. And recently we had a top student at WITS, which we presented her with a prize. Long-term plan, we're looking to have research engagement to promote research and engage with universities and other research bodies in South Africa. We're also looking to strengthen our communication with the members and inform the members of our activities and new updates that are happening in the industry. We have seen a bit of a gap where some of the standards in the SABS are updated, revised, and that hasn't been really communicated to members. So that's one of the focus areas where we're going to strengthen SSDChair Structural Division's presence in these SABS committees and also engage our members in terms of seeking the input when these standards are published or they're going for public comment. If you have any further questions or you like to be part of the division or assist in any way, please feel free to drop me an email. That's my email address that you see at the bottom. With that, I'm going to introduce our presenter. Our presenter is Mr. Rishan Manilal. He is Head of Engineering for Hilti South Africa, and he holds a BTech in Civil Engineering. He's a member of SAICE, and he has been involved in the development of the SABS standards, and in particular SANS 51992 Part 4, which he's going to take us through the presentation. And that's with that, I'll hand over to Mr. Rishan. Thank you.
Thanks for the introduction, Paiman. Good evening, everybody. Debbie, can you let me know when you see my screen?
Yes, it's there. Thanks very much, Roshan. All in order.
Fantastic. Good, good. So let me actually start with a little story. Paiman, I told you this earlier. You WhatsApped me earlier and you asked me how I'm feeling about the session today. I told you I'm a little nervous. Debbie then called me afterwards and told me the amount of delegates we're expecting. And then I went from a little nervous to very nervous. Well, on that note, though, I really want to thank everybody on the call. I'm just looking at the participants and the numbers, and I really appreciate, and I think on behalf of SAICE, we really appreciate you taking the time to join and learn more about a very apt topic, very important topic in this time in South Africa. To touch on what Paiman said, there's a code in the country now which deals with the design of fasteners into concrete. And what I'll be covering today is part one of this overall very big and complex topic. The title of the presentation is Advanced Concrete Connection Design. This is part one, a general overview. An informal title can be Anchors 101, right? So before I start, I just want to maybe tell you more about me and the company I'm presenting here on behalf of why Hilti and who are Hilti. I think it's a common perception in South Africa specifically that Hilti is known for power tools, and how are we involved in anchors and in connection designs and in codes and so forth. I'm going to give you a quick background though, just to tell you where we came from and what we do. So the company was created in 1941 in Liechtenstein. It's a tiny little principality on the border of Switzerland. It's still a family-owned business held by the Martin Hilti Family Trust. And we like to consider ourselves one of the more innovative kind of companies in the construction industry. We market products to building professionals, to the engineering community, and now established in more than 120 countries worldwide. 27,000 employees in the company, of which 2,000 of which are engineers. I'm one of them. And we have a pretty unique sales model. One thing you probably notice is that you walk into your typical hardware store and you don't see many Hilti products on the shelf. It's because of this direct sales models that we embody. It's about these kind of conversations, the introductions that we're having today. It's about understanding what our customers and clients' needs are and finding a solution to meet those needs. Hence, some of you on the call might have seen us in and around sites, either our engineers or sales reps. It's hard to mistake who we are. We're generally wearing bright red shirts, but that's us in a nutshell. Now, back to the engineering aspect of it. There's a few ways you can get a hold of us. Telephone and the internet, you can go to our website. There's lots of information on there. This direct sales model leads to conversations that we can have with you at your office or trainings like these. And then on the job site, as I say, lots of bright red shirts on there offering support and training and making sure that the solutions that we offer are implementing correctly. Now, enough about Hilti. Let's maybe go on to why we are here today. And the topic is not a Hilti topic, but it's an engineering community topic that we're going to be touching on. And this topic is based on what you're seeing on your screen right now. SANS 51992-, a new code that was published in March, and a code that is very important to the engineering community and very important for us as some of the members who help drive the code to create awareness and create education on it. Now, this code, SANS 51192-4, is based on Eurocode. So as you can see at the top there, SANS, and then below that EN 1192-4. So that's Eurocode 2 Part 4. It's an exact replica of Eurocode, and I think that's a good thing. Eurocode 2 Part 4 and Eurocode as it's in itself is one of the most advanced codes in the world right now. And for us to have that as part of our standards, I think is only a good thing. Now, it wasn't us that pushed this code. This is actually something that came from a committee who's done a lot of hard work in the implementation of Eurocode in South Africa. They're still working on other parts, but how this specific part 4 came to light was there's been a few failures, I would say, over the years from an anchor perspective that led to, unfortunately, injury, death, and damage. And this resulted in this code being fast-tracked through the system and being implemented. The committee, as aforementioned, has been working for years to implement Eurocode. They roped specific stakeholders in the industry, us, some of our fellow anchor suppliers, and together we collaborated and discussed what would be the best route forward. And this code was then published in March. Now, behind this first page, there's another 140 odd pages of lots of information, lots of calculations, lots of equations that we could go through. But that's not the purpose of the session. This, as I said, is Anchors 101. And let's maybe start from the foundation and build from there. All right. So like in many other fields of life, there's common bad practice and examples in the construction industry. I'm sure each of us on this call as engineering professionals have noticed some of them. And this could be down to a few reasons. Not understanding the requirements on site, not using the best tool, not choosing the best solution, and not complying with rules and guidelines for the aforementioned code. Now, none of these pictures were taken in South Africa, so I think we are ahead of wherever these specific scenarios occurred, but there's still a bit of things that we see on site that can be done better. Now, with these many delegates on the call, I see there's over 400 of us here, and I'm assuming most of us are engineers, civil engineers specifically, and we realize that we can't make some of the mistakes that we saw in the previous page, because professional decisions do not allow doubts or mistakes, because the consequences can be very serious. I mentioned before that that anchor failure in the past has led to the implementation of this code, but we specializing in anchors at Hilti, I'm sure with you engineers out there, it's not just the anchors that you have to consider, it's everything surrounding that. It's the entire structure and ensuring that we do things safely and do things per regulations is critical. Hence the reason that I wanted to start from basics on this topic. Before diving into the code, it's important to firstly understand what are anchors, what are the different principles behind them, and how do we use them in the industry. So fastening systems can be split into two solutions. Cast in place installation, self-explanatory. The anchor or the fixture is cast in with the concrete when it is poured. And then post-install installation, which can be split into two criteria. Direct installation, typically your nail guns and what we at Hilti call direct fastening solution, where a fixture is shot into the base material. And then anchor installation or post-install anchor installation, which is the systems that we'll be focusing on during the course of today's session. Now, most of you on the call would have looked at a data sheet for an anchor, whether it's a Hilti data sheet or any of the data sheets for any anchor out there. And you might wonder how these small, tiny little metal fixtures can resist such high tension and shear loads. Well, this resistance comes from three working principles: friction, keying, and bonding. Friction is the tensile load is transferred to the base material by friction built up by the anchor expansion. I'll touch on that a bit more just now. Keying, during the setting operation, an undercut is created that transfer the tensile loads like a cast-in headed stud. And then bonding, the cured mortar mixture creates a bonding between the anchor and the base material. Now I'm going to show you exactly how these principles work. I hope my video can be seen. Now, this is the friction principle. As you can see, there's a little metal element at the bottom of the fixture that expands as you torque this anchor. And with this expansion, it creates friction with the concrete, which gives this anchor its resistance. The principle of keying, I'm playing a video now, has a sharper element attached to this anchor. And this sharp element, while torquing the anchor into the base material, cuts into the concrete and it's almost self-taps itself in there. And this keying effect gives it its resistance. And then finally, the bonding principle, which involves a metal element with a mortar. And you first drill a hole, make sure it's clean, and install the mortar. And this bonding between the mortar and the metal element, and the mortar and the base material gives the anchor its resistance. Now, two things I want to specify here before we move on. We spoke about bonding and I mentioned cleaning. And this is one of those going back to best practices and safe installations on site and doing the right thing if we understand it. A basic principle, the mortar bonds with the anchor, the mortar bonds with the base material. In order for it to bond with the base material needs to be cleaned correctly. And hence you'd find any bonded anchor, you would see whoever you're purchasing them from, you would see that cleaning of the boreholes are extremely critical because dust can negatively affect this anchor. It's the same on the friction side and the expansion side. I mentioned torque. The anchor expands with torque, and every expansion anchor that you might purchase or specify will have a torque requirement. If it's over torque, the anchor will expand too much and can cause damage within the concrete. If it's under torqued, the anchor can displace, which could lead to failure. So a couple of safety requirements that you would need to look at when specifying and looking at these anchors on site. Now we speak about these principles. We can also group them into two separate compartments. On the mortar side and with the bonding principles, we have chemical anchors, which is the common name out in the market there. Chemical mortar, chemical anchors, epoxy sometimes. And on the right-hand side, we have mechanical anchors, which can be split into two further categories. Metal anchors, more for your structural connections, and plastic anchors, typically non-structural, mostly to hang up wall frames and other stuff. Good. Now, chemical anchors can be broken down even further. And I want to touch on this a bit more because there's further principles that we need to consider when assessing these anchors. There's bonding, right? We spoke about the fact that it bonds with the rod and the concrete base material. And this is almost like a technology in a way. There's a micro keying effect that occurs with specific chemical mortars. And this is based on the makeup of that mortar. It finds little crevices in the base material and it attaches itself to that. And through that bonding, you can get amazingly high load resistance. Then there's bonding expansion. This is a fascinating principle and actually pretty new technology. You see the rod in these cases are not your typical threaded rods. What these anchors do is actually the rod itself, once torqued, breaks its bond with the mortar. And once the mortar is cured, when this anchor is being resisted or a tension force is applied, it pushes outwards. It pushes against the cured mortar. And this mortar in turn pushes onto the base material and gives it really good resistance. There's a few anchors like this in the world, and these are the only anchors that you can actually, or only chemical anchors, I should say, that you can actually use in an unclean hole, because it actually uses the principle of expansion and friction to give it its resistance. And then finally, we have hollow masonry. I want to just show you a video of what this looks like, because this is a fascinating principle, because anchoring into masonry can be complicated sometimes. You generally need to consider the fact that there's crevices in there. And as you can see in this case, the anchor needs to be used in conjunction with a sleeve. And that sleeve is perforated. When you install your mortar and apply your rod, the chemical or the mortar protrudes out almost like a cauliflower, I like to say. And this gives it a keying effect in the hollow masonry, which gives it its resistance. Oftentimes you'd find if an anchor like this fails, it's usually the masonry that fails and generally not the mortar. Good. Now, we've covered the type of anchors that we have out there, the principles that we have to use when we look at how they are installed in these base materials. Now, there's other influencing factors that you need to consider before you even start any design for an anchor. The first is the base material. I mentioned it a few times already, concrete and masonry being two of them. The second is the loads acting on the fixture. The third is the environment the fixture is being installed in, super critical. And probably the most important consideration, geometry. Where in this base material is these anchors fixed? How close are they fixed together? Let's look at the base material aspect. So anchor applications can be required on several different types of base materials. There's many types out there. There's concrete, solid masonry, timber, natural stones, and each of these base materials might have different requirements, and that's due to a couple of things. The obvious ones is that they're all different in composition. At the same time, they all have different resistances and different strengths. And this needs to be considered when selecting an anchor and when designing an anchor. I often like to say this, it's when it comes to anchor design, it's never a case of one size fits all. We need to take a step back, look at everything, and then we can start the design process. For the purpose of today's session, we'll be focusing on the concrete and masonry aspect of fixing. So, as I said, not a case of one size fits all. In terms of mechanical anchors, they generally can only be used in concrete and solid masonry. Even in solid masonry, it's never ever recommended that an expansion anchor should be used. It can cause damage to the masonry, and certainly can't work in hollow masonry, because if, as I showed you earlier, if the expansion element is sitting in the hollow part of the connection, can cause some issues. Chemical anchors, on the other hand, based on its varying principles, can work in all three types of base materials. And finally, rebar, an obvious one in concrete. On the topic of rebar principles and anchor principles are completely different. So from a design perspective, you cannot use the rebar principle to do anchor design. That's a topic for another day. Good. I'm going to spend some time on this slide. This is actually pretty critical, and something that we as an engineering team also like to drive and inform the engineers that we deal with. It's the cracked concrete concept. And when I say cracked concrete, the obvious thing that comes to mind is us walking along site and we see some cracks on the concrete, and that for us could be cracked concrete. Yes, it is theoretically and technically and obviously cracked concrete, but from a cracked concrete principle in terms of anchor theory, that's concrete that has failed. That doesn't work. The cracks we're talking about here are cracks in the tension zone of the concrete. Now, we all know, and you can see in the simply supported structure here, that this beam of concrete takes compression, and the rebar at the bottom of this beam or the slab will take up the tension of the forces acting on it. But what happens within those rebar or between those rebar is that as it takes the tension, it's natural for micro cracks to form within the concrete of these tension zones, right? So it's not cracked concrete that's visual, it's cracks that form, which is natural for it to form in tension zones of concrete. And this has a significant effect on the performance of an anchor. And it's something that should be one of the immediate considerations when starting an anchor design. Is this anchor being installed in the tension zone? And as you can see now, I've removed that simply supported, and things change, but there could be some flexure in your column. There could be some bending moments in this beam that creates tension zones on the top and the bottom. And the rule of thumb is, if we're unsure if this anchor is being installed in a non-crack zone, then we should automatically assume it as cracked concrete. And why I'm highlighting it this much is that you might look at technical data and you'll see sometimes for anchors that have approval or is approved for use in cracked concrete or is approved for use in tension zones, there'll be two tables on there. There'll be one for non-cracked, one for cracked. And when you get a chance, go look at the differences in the design resistances for these anchors in those zones. It's significant and can have a drastic effect on your design overall. Just an additional point here I just want to make. There's actually countries in Europe that don't allow for designs in uncracked concrete. It's part of the regulation that every single anchor design is done in cracked concrete. We're not at that point yet, but it's just something that you should consider when doing an anchor design. Good. Now, second influencing factor that we need to consider, loads. And this is big responsibility of ours as engineers to really understand the type of loads that's been exposed or the type of loads these connections will be exposed to. The common ones and most common ones that we allow for are static loads. It's wind, it's snow, it's the self-weight of the structure. And that's something that we calculate through our structural analysis. There's other loads though that need to be considered, and these are super critical in terms of choosing the right anchor for the right application. Now, they can all be referred to as dynamic loads, and there's only specific anchors in the market that has approval for dynamic loads, and you would see that in technical data or ETA of the specific anchor that you choose. Dynamic loads that we have to consider is seismic. If we constructing or if we're building in a seismic area, we need to take this into consideration that the anchors also need to be considered when it comes to seismic design. There's shock in any barrier on a highway that could be hit by a vehicle is an example of shock and the specific anchors that has shock approval. And another important one is fatigue. This is often used in the industry side of things. Machine equipment is a good example of an application where anchors need to be designed with fatigue approvals, or fatigue needs to be considered when designing these anchors. This constant movement of the machinery can lead to long-term creep of these anchors. Finally, and becoming more and more important over time, is fire resistance. And the most simplest way to explain this is that, firstly, specific anchors have approval and can be designed when it comes to fire. And just imagine a building where you've got heavy pipe supports needed for your sprinkler system. Fire starts and sprinkler system kicks in, but the anchor fails. That sort of defeats the purpose and creates more problems than the sprinkler systems putting the fire out. So an important consideration, topic that's becoming more and more viable, is fire resistance for anchors. This is something that needs to be considered when looking at the loads. I really like this slide, and I think this is where I bring back the story of sort of one size fits all. Now, these are from a dimension perspective and properties perspective, these are 4 identical anchors. They all M12, they all have the similar embedment depth. And the only difference is that they're using the various different principles that I just discussed a little earlier. And you would see that for each one, the tension loads from a design perspective is pretty similar, but the shear loads is quite different. So again, understanding the application, understanding the loads, understanding the approvals needed for these anchors is critical before we get to the start of our actual design. There's something else I want to point out. This M12 here, the stud anchor with a red band on it. We have 4 identical ones in our portfolio. One has a blue band, one has a black band. And you can put them all next to each other. They will look exactly the same. But only one of them can be used in cracked concrete. It's the one with the red band. The other 2, it doesn't have approvals for use in cracked concrete. We would never recommend its use in cracked concrete. It's the same from a loading perspective. You can compare their design resistances, and you'd see there's significant differences between those three, but they look the same. And hence, the approvals of these anchors, very, very important. Good. Now, the third criteria that we need to really consider, environment. And in South Africa, with the coastal cities and the coastal towns, this is a very apt topic. So there's typical ISO corrosion handbooks out there, and anchors follow the same criteria in terms of ISO requirements and the requirements in these corrosion handbooks. Internal areas where there's generally dry conditions, typical zinc coated anchors are fine, or we call them galvanized in South Africa, fine. If there's a chance that these anchors can be exposed to atmospheric conditions or damp external conditions, stainless steel must be considered. I mean, you see an example here of seating in a stadium. It's outdoors, it's exposed. The stadium could be Moses Mabhida right next to the ocean, and stainless steel must be used. The zinc anchors would not last its design life. And then finally, at the bottom, you see a swimming pool. And I can tell you guys an interesting story regarding this one. There was actually a failure. I'm not sure where in the world, but we did an investigation on this. And the roof at the swimming pool actually collapsed. And stainless steel anchors we used, initially, they couldn't figure out what was wrong. And the concept came that, or the report showed that when we did our analysis, that the chlorine from the swimming pool affected these stainless steel anchors and actually corroded stainless steel. So it's not sometimes easy to figure out everything, but these things need to be considered. If there's chemical exposure or if there's gases in the area that can promote corrosion, you have to go above stainless steel, and it's called HC. We call them HCR anchors, high corrosion resistance anchors. These are very, very, very specific scenarios that you need to use this. But again, an example would be a swimming pool where there's not just water, there's also chlorine, and that can affect these anchors from a chemical perspective. Finally, and as I mentioned before, one of the key criteria to consider is geometry. And this is where code is important, and I'll touch on that a little later. But a couple of factors that we need to consider when looking at geometry. First one is the type of installation. The second one is the thickness of the fixture. This is typically your base plate, because if you're using a mechanical anchors, which come in standard length, the thickness of the base plate can affect the embedment depth of that anchor. And then the third one is edge and spacing distances. I touched on this earlier, and this is extremely critical. And when we get to that point where we're doing designs, you would see how this affects your design from a load capacity perspective. Now, I want to touch on something, and this is something where we're moving more towards the code now. We've done all of these background research in the environment. We looked at the type of loads. We looked at the base materials. We got a good understanding of it. We're now getting into the actual designs. And the reason an anchor design is not easy to do by hand, it's because each of the following failure modes need to be calculated for when doing that design. And each of these failure modes is in SANS 51192-4, Eurocode 2 Part 4. These are all designed for. The first one is concrete cone failure. It typically occurs when the embedment of the anchor is not deep enough to resist the load required. You'd find that a huge cone of concrete will pull out when this fails, or if this fails. Sometimes can occur when the anchors are also spaced too closely to each other. So it creates a huge influencing factor on the concrete and results in a massive cone failure. The second one is pull-out failure. Again, could be resulted by the chemical anchor not being deep enough or not being embedded deep enough to resist the load, and the anchor itself pulls out. So the concrete is fine, but the anchor pulls out. The third one is edge failure. Again, through geometry, an anchor can be too close to the edge or spaced too closely together, and a shear load or a shear load combined with a tension load would result in edge failure. This is actually quite a common failure mode in the industry. Third one is steel failure. instead of using an M10 anchor, instead of using an M20 anchor, we might have used an M10 anchor, and the shear loads were pretty high. Might result in steel failure. Splitting failure, this generally occurs when the base material is not that thick. If you're only embedding into a 100 mil thick base material or 100 mil thick slab, it can result in splitting of the concrete. And then one of the shear failure modes is pry-out failure, where the concrete behind the anchor actually fails in the direction of the shear force. This is not something that we're going to have enough time to go through in detail in this session. This is when we go through the design itself in the code, which is anchors 202 or 102, but we'll get to there eventually. Now, I touched on a few criteria that we have to look at. I touched on many different aspects that's pretty general that we have a job to do as engineers to make sure that we can cover. And I also touched on the fact that there's a big 140-page code that we need to understand when it comes to doing these designs. I highlighted safety and failures. And the truth is, it's not just safety and failures that we see out there. Safety is critical. It's the most important thing when we're doing any design. And looking at these typical applications here, some of them we really have to consider safety as being pertinent. Facade fixings, for example, and steel and metal in construction. But there's another thing that happens out in the industry is that based on our inclination to be safe, we can over-specify. What I mean by that, there might be typical balustrading, for example, applications, or typical small little tiny canopy applications that we would specify a M20 anchor when an M10 anchor could have been more than sufficient if we had designed correctly. So as I say, if I compartmentalize, safety is critical. The code provides safety, but at the same time, it also gives us a chance to optimize our designs so that when contractors purchase this equipment and purchase these anchors, they're not spending more than they should. We make our projects a lot more cost effective, and everyone's happy at the end of the day. Good. Now, a deeper dive into the design part of it. There's 3 essentials for any anchor design out there. And our code, which is based on Eurocode Part 2, is the first aspect. It's a design method. Remember, I mean, prior to March this year, we had no code in the country, and it was our responsibility as engineers to make sure that we're using the right design method when doing the design. We now have code, so we have something that we regulated by. So the design method is critical, but together with the design method, you need technical data. And this is not technical data, for example, that Hilti can provide to you, because we can test our own anchors and tell you that it's the best anchor in the world and give you a stamp of approval from Hilti. But in order to do a design, that's actually not good enough. You need an anchor that's approved by a third-party organization, an institution that does these tests in accordance to specific standards, and they will tell you whether this anchor is seismic approved, this anchor is approved for cracked concrete, and the design load that this anchor is safe to use with. And that's called an ETA in this case. And in South Africa, we are now obliged, in line with Eurocode 2, to use anchors that have approvals with the ETA. And I'll be honest, not all Hilti anchors are approved by the ETA. It's not a good thing, but 98% of them are. And I think with our competitors out there, they also have many, many ETA approved anchors. And the ETA gives you that assurance as an engineer that this anchor has been tested extensively, and the information in this document can be trusted. It wasn't done by the supplier, it's done by a third party, a reputable third party. Now, the final thing that you need when doing a design is load definitions or expected loads. And this comes from you as your engineer. You get your loads from Procon and the various software. You find out what the reactions are at that connection. And then using the information from the ETA, following the design method, voila, you have your anchor design. Now, I want to touch on a little bit more on the ETA. As I said, it's a third-party organization. There's lots of information in there. And I've gotten to the point where I've starting to ask my engineers to not share our own technical data with Hilti at the top, even though the information in our technical data is a consolidated version of the ETA. Don't add anything different in there. I'd rather send you guys ETAs. It's a lot more comprehensive, but it has all this information in there that gives you specific insight into what these approvals have. And then finally, as I said, and to repeat myself, you have a trusted source of information that you can use. Good. It's not just ETAs though. As I say, Eurocode 2, which is a great code that's been adopted here, but the American code, for example, ACI 318, if that had been adopted here, we would have to use ICCES approved anchors. So that's the North American institution that does these tests, and they issue these certificates based on the approvals on these anchors. Now, the scary page. We used to have interesting conversations, and I don't know if any of my former, not former, I would say, any engineers who's in the audience I've spoken to before. I used to be a field engineer on the field when I started at Hilti 4 years ago, so I might know some of you in the crowd. And the big discussions we used to have sometimes is around safety and who's responsible for what, and where does the supplier's liability lie, where does the engineer's liability lie. With code and in our documentation, or our local building documentation, yes, the suppliers take a lot of responsibility if there's product defect. But from a design perspective, National Building Regulations and SANS 10400 both speak to the competent person doing a rational design. And that moves liability to the individual who's going to specify the solution in the drawing for the contractor to install. And this needs to be done safely. And that's where I'm really, really happy that code is now around. Having this regulation, it means that there's a standard across the country that everybody can use and everybody can be guided by. I mean, in university, I don't recall, I don't know if the syllabus has changed, but anchors were never really touched on as part of the syllabus. We were focusing on bigger things like reinforced concrete and structural steel and structural analysis and so forth. Anchors are a very small part of the overall big picture, but safety-wise, it's one of the most important parts. And as you can see in these two, I'm not going to read through it, as you can see in these two extracts from the National Building Regulations and SANS, the liability comes back to us making sure that we are doing a competent, rational design, either based on a standard or based on a suitable design methodology. If it didn't exist in the country, which it didn't before March, we would have had to find the suitable design methodology and follow through on that. But I just want to point out, it's not all doom and gloom. And I'm coming more towards the end of the session, and I want to just touch on what we can look at moving forward. There's easier ways to do this. And the first thing we'll look at in follow-up sessions is understanding the code from a deep dive into it and looking at these various failure modes that we need to design for. The other thing is, if you had to do an anchor design by hand, and I would be nice to hear from the audience if anyone's done that, you're looking at between 2 to 3 hours to do it. So we obviously don't have 2 to 3 hours in the session. Debbie might kick me out if I go on much longer. But what we'll use is there's a software freely available from which we can then do some designs. We can then look at it and pull out extensive reports. And all of this can be done in 10 to 15 minutes. The software is based on Eurocode 2 Part 4, so there's no black box feeling where you're not sure what information you put in. The report that comes out of the software references specific codes in Eurocode 2 Part 4, and that'll form part of our follow-up sessions. And finally, once we do this example together and do this actual designs, we will then go into a bit more detail on the various failure modes and the utilization of these anchors against those failure modes. And I don't want everybody to feel scared or lost or confused leaving this session. I mean, I'll share some links after this. You don't feel intimidated by this topic. It's a initially might seem complex, but it's pretty simple principles, pretty simple methodology. And there's also very useful tools out there that you can use to do these designs. And again, I'm speaking in, and I say, it's not a Hilti thing. We've got software that's freely available on our website, and so do many of our fellow anchor suppliers. They also have these materials available. The big thing for me is education on the code, is you as an engineering community feeling comfortable designing, following this code, and ensuring that we have safe connection designs out there. Cool. Questions. I will share some links just now, and as you guys ask some of the questions, I'll share some information with you, which I'll present. But Debbie, I think I'm well within time.
Absolutely, yes, Rashan. Thank you so much, because I think we're all worried about load shedding this afternoon.
Yes.
Can I take you through some of the questions that have been asked? I see that Sanjay has made a comment about a new product from Hilti, which has been launched where you don't need to clean holes for anchoring. Is there anything else that you want to add? I see that Erbert has provided a response.
Yes. I'm not sure what Erbert said, but yes, there is. It's called a HIT Z rod, and it's one of the few chemical anchors in the world, as I mentioned before, and I'm going to take you guys quickly back to this slide so we can just touch on that. This can be used, sorry, it's the wrong one. It's this principle here. So very specific rod used with the mortar, and instead of using the bonding principle, it uses the bonding/expansion principle, where the rod itself actually breaks its bond with the mortar, and the way it's designed pushes outwards, and that creates friction between the mortar and the concrete element of the base material. Hence, it doesn't matter if the base material is dusty, you're not depending on the bond, you're depending on the expansion.
Thanks
Hope
very
I answered
much.
the question.
Okay, Sid is asking, what is the best way to deal with clashes with rebar?
That's a fantastic question. And there's, if I can be honest, Sid, there's no, I'm not going to say there's no solution. There's no solution out there that an engineer will be completely happy with. So the first thing we can do is see if we can move the position of the connection. If we can do that, then that's amazing. You avoid destroying any rebar in the concrete, and you have a safe connection in place. But if you design an anchor, and if you come up with the required embedment depth, in order for that anchor to resist your loads based on your design, you need to meet that embedment depth. I've oftentimes seen people cut off rods and go with a shallower embedment depth and try and save the rebar that's in there, but that now gives you an unsafe design. So first thing, if we can move the connection, first prize. If we can't move the connection, we'll have to make a judgment as an engineer whether we cut through that rebar. And I know engineers hate hearing that. There's drills and there's coring rigs available that you drill through. But again, it all comes down to geometry, and it all comes down to safety. And if you have a required embedment, unfortunately, you have to meet that embedment depth.
Okay, we have a question here from Creason. He's asking, what are the solutions if we are restricted on edge distance?
So when we look at the next part, and we'll go into that in the follow-up session, there's an alternate design that we can do. So I mentioned that we have engineering support. We also have engineering support up in Dubai. So we have a PMO team. It's a feature that's going we're trying to build into the software. It's a little outside of code, but it works with sound engineering principles. And this is again where we have to make an engineering judgment as engineers out there. So it's called utilizing rebar within the edges of the concrete. So where you have edge distance or you have a high shear loads, there's certain minimum criteria that you can't cross. Every anchor you see in the data sheet has a minimum edge distance, and it should never and it can never be less than that. But you can find methodologies where you can utilize the presence of rebar to resist higher loads, even with that minimum edge distance. As long as that minimum is not crossed, then you can work around by utilizing the rebar. But we have to understand what the existing rebar is in place, and based on that information, we can do a design and check that out.
Okay, next we have a question from Dane, who's asking, does the code pick up on strengthening through supplementary reinforcement?
That's exactly what I just spoke. Thank you for that
Yes.
question. And I was speaking about supplementary reinforcement in the previous answer. The code doesn't touch on it. It's more an engineering principle that we need to follow. The code, so just to divulge, but the previous code was called ETAG. It's been evolved into Eurocode. And like any code in the world, as we experience things in the market, the code evolves with it, right? And Eurocode was launched in Europe a couple of years ago. And they actually looked at this rebar concept and supplementary rebar. And they actually removed some of the safety factors from ETAG that they what do I say? They were a little bit conservative with, and you'd find now with Eurocode 2.4, you can utilize rebar a lot more. But a supplementary reinforcement design is a different design and something that we can assist with, but we have to understand what the existing reinforcement is.
Okay, next up we have Sanjay, who's asking if your anchor is well within the rebar cage, do we need to consider the edge distance criteria?
Yes, edge distance will always need to be considered. JB, I'm going to quickly just show something here. Sorry. So this is sort of what the software looks like, and when you design, regardless of where the anchor is, if it's positioned close to the edge, the minimum edge distance has to be adhered to. It's part of the code. It is there. Even if there's sufficient reinforcement, minimum needs to be adhered to. So, yeah.
Okay, Ilana Forbes has asked, does the code cover the fire resistance of the anchors, or how to ensure you achieve the required minutes?
Yes, and that's a good question. That's a great question, and we can dive into that in future sessions. But the code will cover that, and it's more covered in the ETA information and the technical data of that specific anchor. So when you're designing for anchors, so for fire resistance, understanding what the requirements is from a fire perspective is the first thing, and then using that information together with the code, you can do a design. You can actually do it on the software.
Tabanga's asked, how does anchoring affect the structural integrity of mass concrete?
For understand the question correctly, so if we're looking at anchor failures, it shouldn't, right? It's generally small diameter of anchors placed in large, huge concrete elements. The one time that I could see where anchoring can affect it is if there's splitting failure. If the concrete is really thin and we're trying to fix into that concrete and we then apply a load to those anchors, it could result in splitting of the concrete. But all in all, it doesn't affect the integrity of the concrete, unless there's failure. And failure generally comes from not doing the design.
Hannes Lewis has asked, when must one fill the gaps between bolt and hole in plate with solid epoxy?
Wow.
For example, in a 4-bolt connection under shear loads.
What a question. That's amazing. This person, thank you for that question. And I hope, if not a Hilti engineer, an engineer from another anchor supplier spoke to you about this concept. It's a fascinating concept, and I'll use this model to show you. So any base plate, if you have anchors in there, you generally will have a bigger hole diameter in your base plate than the size of the anchor. For example, an M16 anchor, you'd want to have an M18 hole or maybe even an M20 hole on your base plate to make sure, because you're going to move this base plate around a little bit to make sure everything fits in there. And by having that, you're going to have a void between your base plate and your anchor. And for tension loads, that wouldn't matter much because those anchors will be bolted down onto those base plates. But for shear loads, you could have displacement of the base plate if the anchor is not sitting at the center of that hole, right? And the base plate relies on the shear force will be applied to the steel member. The steel member then transfers the load to the base plate, and the base plate needs to transfer the load to the anchors. Now, if the anchor is not sitting flush against the base plate, then you could have some movement there which could be detrimental. So to answer the question, whenever there's a shear load and you have more than one anchor on the base plate, you need to fill those holes between the base plate and the anchor to make sure that the forces are transferred uniformly from the base plate onto these anchors.
Trevor Duncan is asking, does the code make allowance for anchoring with competent rock? Is there a definition on what competent rock is? Or is it a requirement for geotechnical, sorry, something's happened here on my screen. Or is it a requirement for geotechnical specialists to confirm?
Great question. Rock is one of the enigmas of base materials. It's the challenge with rock is, right? So we spoke about different base material, but 25 MPa concrete is 25 MPa concrete anywhere in the world. And as I said, each anchor needs to be sent to the ETA. And what they do is they will install these anchors in 25 MPa concrete, 30 MPa concrete, and they will give you data which will be relevant throughout the world. The challenge with rock is it differs across the world. And the code does not cover it just purely because there's no ETA for anchoring into rock. What we suggest is, and again, this comes down to engineering judgment, and what we do for engineers is, if we don't know what the rock is, and we have done some tests in specific rock types, which we can share. If we don't know what the rock face is, we go out to site and we actually install some anchors and do some pull-out tests. Based on that, we can judge a safe design resistance, and together with the engineer, make an engineering judgment on what's safe and what's not safe. So best solution, go out, install some anchors, do some pull-out tests, check what the design resistance is, and apply some safety, and then we can design safely that way.
Okay, next up is Rowan. He's got quite a comprehensive question regarding holding down bolts. Let me just go through this here. Holding down bolts for canopy warehouse structures exposed to uplift wind effects. The previous SANS codes specify the use of cast and holding down bolts with anchor plates. We have used Hilti chemical anchor bolts for small canopy structures and pipe supports. How would we go about selecting a suitable anchor for large warehouse structures, for example, 60 by 30 meters. Are these specifications provided in SANS 51992-4/2021?
So again, a very good question and very apt because we come across this quite often in the industry. So the first thing is, I want to touch on the 3 requirements: code, ETA, and loads. And here we have to look at the loads aspect. And we could do a design here on the screen right now and make this edge distance really small. And we know that the uplift and the loads in structural steel warehouses for big connections pretty high. If the loads are too high, the post-install anchor connection it will fail. And there's one thing we won't do is give you bad advice. If it fails, then the holding down bolts, due to the fact that it can go much deeper, might be or will be the better solution. In terms of the code, so the code does speak to holding down bolts, but this is where the other aspects of Eurocode that the committee is working on will need to come to the fore, because our local concrete code and the way it talks to holding down bolts is different from what SANS 51192-4 or Eurocode 2 Part 4 talks to holding down bolts. The requirement here, or the requirement is in Europe, is that holding down bolts needs to be designed like a post-install anchor would, which doesn't fall in line with the local concrete code in South Africa. So to bring the story short, long story short, the code is for post-install anchors. If the loads are too high, then don't use the post-install anchors and stick to what's allowed, which would be the holding down bolts. And I've done many designs that unfortunately we couldn't provide a solution for due to the high load requirements. And again, as you can see, you can choose Eurocode 2 on the software. This will give me all red on the right-hand side and tell me this doesn't work, the tension is too high or the shear is too high, and you're not going to find a solution.
Alan Fodden is asking about insight testing the pull-out strength of a previously installed anchor using a torque wrench. Have you got the questions in front of you, or can I just continue reading them? A torque wrench on a nut and bearing onto the concrete surface is practical and simple. Do you have any rules to apply to this test?
I do not fully understand the question. I'm going to try and find it here.
Yeah, it's Alan Fodden. You can see we've got many questions lined up for you still.
Oh, there you go. Okay.
Yes.
Okay, so this is an interesting question, Alan. So if you look at most technical data sheets, there's specific torque requirements for an anchor. For mechanical anchors, there's a set torque. I'll give you an example. I know a stud anchor has 80 Newton meter torque for it to be set perfectly. So to try and test this anchor, for example, by using a torque wrench, could actually damage the anchor itself and cause some damage to the concrete because you're over torquing it. In the case of chemical anchors, there's no real torque limit, but there's no real torque requirement, but there's actually a torque limit. So by over torquing an anchor, and it's all in the technical data or the ETA, and if you exceed this specified torque, you're applying much more tension, and you're also causing the bonds to break between the chemical and the wall. I wouldn't recommend this method of testing. There's other rigs that you have that does tension pure pull-out tests that's connected to hydraulic gauge, and the gauge will give you the tension much more accurately.
Ed Hennessy has asked, what about eccentricity on the HD bolt from the gap between the concrete and the underside of the base plate? In other words, the packers that make up the level differences between the underside of the base and the top of the concrete foundation.
Good question, and we call that in the code, it's referred to as standoff. So standoff between the base plate and the concrete. And this does affect your anchor design. We can check that here. We can add standoff with clamping, without clamping, and with grout. And when we do an example, and it's free to reach out and we can chat about this, when you start applying loads to this, especially in shear, you'd find because of the standoff, there's a moment created on the underside of the base plate and the anchor and the concrete. And due to this moment, it results in substantial differences in the resistance that it can have. So as you can see here, I'm adding a 50 kilonewton shear load to this connection with a very high standoff of grout, which is 30 mil, and it completely fails. If I remove the standoff, it moved from 600% to 125%. Listen, we can play around with the anchors. This is an M12 anchors. I can play this and make it 16 mil, but the standoff has a big effect. It's because of the moment created at the underside of the base plate. And when you design it, you have to consider standoff.
All right, Rashawn, I'm going to take our last question, which is from Dane. Does the code deal with dowel action and anchors under shear? In other words, additional bending stresses? Does it allow for reduced dowel action if the gap between the base plate and base material is filled or grouted?
It's similar to what I just explained now. So we kind of covered that. So you can actually now, and again, this is where the code evolved. There was a lot more safety factored into this when ETAG was the code across Europe. With Eurocode 2, you can actually change the compressive strength of the grout underneath the base plate. And this can help your design. But at the same time, it still considers it a moment. And with grouts changing across the world, there's huge safety factors in the equations of this, or the calculations of this in place that I would say leads to this kind of output. I often tell engineers when it comes to grouting underneath the base plate, if they need to make an engineering judgment on that, if they're comfortable with the way it was installed, because the safety, when you look at the code, the safety factored in here is more because of possible air voids between the grout and the base plates, and these voids can lead to massive moments being applied and bending of the anchors itself, which is a concern. So if the engineer is comfortable with the way the grout was installed and the quality of grout that was used, we can make a judgment when it comes to these kind of aspects.
Okay, thanks so much, Rashawn, for answering those. There are quite a few more, and I suggest that I'm going to take a copy of all of them, and we can maybe post them on LinkedIn to be answered, if that's okay with you. Yeah, please. If you could consolidate them, Debbie, send them to me. I'd be more than happy to reach out and answer. I just want to quickly, I told Pam, I'll share this. If you've got questions, there's a free platform that we have. We have a team in Dubai of engineers that will answer your questions on this platform. It's called Ask Hilti. So you can go to askhilti.ae. It's a community we created that gives us some access to engineers, especially in remote areas. And you can log in here, ask a question, and you'd have one of our engineers in Dubai answer it for you. If you don't come right to them, let Debbie know, or let SAICE know. They can reach out to us. We can answer them, or you can just contact us through our website, and we're happy to answer and help. Okay, now, Rashawn, we're going to be having another 2 workshops. Is that right? Can you maybe tell the delegates a bit about that? Fantastic. Pyman and I are going to chat after this. We're going to decide whether to do it in 2 workshops or one, maybe much longer one, maybe a 2-hour session, which I think could work, because we were obviously struggled with time today. I wanted to dive into a lot more, and I'm sure the delegates on the call wanted to know a lot more. So I will align with Pyman. We will make a decision on how we do the next 2 workshops. We might do it as one full workshop, and then look forward to SAICE's LinkedIn page to check when that's going to be hosted. I look forward to it. Okay, Pyman, I'm going to hand over to you to do the thank you and the closing.
How do I?
All
Sorry
right.
if I'm.
No, it's okay. It's okay. Thank you, Rishan. This was great. It's actually, we dragged you literally into the next workshops because some of the questions they're already leading us to the next workshops. So thank you again for your time and your excellent presentation. What we do is, if you could share the email with, the link to the Hilti website, to the platform where the members, they can ask directly questions from Hilti. Then in return, we share it with all the attendees of today's session. And then some of the questions, now in the interest of time, they're excellent questions, but we're just running short of time. We're going to post them on LinkedIn with the answers. So we collect the questions, send them to you, and then we'll post the question and the response on a specific LinkedIn post. And further to that, you have Rishan's email address. And if you don't have his email, here is my email. I'm sharing my email address here. So just please drop me an email address, and then I would pass your questions to Rishan. But nevertheless, Rishan, thank you very much. It was an excellent presentation. And I'd like to thank Debbie and Mr. Mulder, and also our attendees for being with us today. And with that, it brings us to the closure of the workshop. Thank you, everybody.
Thank you, everybody. Thanks, Paiman.
Thanks so much, Rishan.
We beat load shedding. Yes.
We absolutely did.